This is much better homework sets than 221, where they'd take me an hour to go through. My other class today, it was a 1 hour study set. So 2 quick comments for you. One is I sent an email yesterday, and so if you want a bonus point, you get to respond. There's a big but to it. The email, you'd have to respond before 4 o'clock in the morning. That's when the lunar eclipse is happening and the clouds are clearing up, so we might see it. I actually am up at that time, so I'm going to be looking. But it's not just replying to the email. You have to have a topic. And so 2 people have given me a topic so far. We originally were going to be doing our presentations this week, and I realized last week that wasn't going to happen. So I'm hoping you guys will have topics very shortly, but this class likes to wait to the last minute. We could honestly do our presentations this week and you would all pull it off, I'm sure, but we'll do them next week. So the other thing it asked in there, I'm willing to do some presentations Tuesday and some Thursday. We do have to have a class in there, but you can decide if you want to respond to it or respond to me. And your presentation is an innovation. So for the lab this past week, those of you who did it, you had to write a page about something. The plastics lab, which most of you did, you had to write a page about something. In the gas law lab, a lot of you wrote about an innovation. So you can just expand on that for 3 or 4 pages. Or you can pick a different innovation. And as I say in the email, our topic that we're going into this week on Thursday is radioactivity or nuclear chemistry. So you could do anything dealing with energy or just any topic that you think is a cool innovation. There's actually been some pretty cool things in the science news in the past few weeks. So, all right. So what is kinetics? The study of? Anyone?
The rate of reactions?
Yes, it's studying the rate of chemical reactions. And so this is a question on your worksheet today. And you'll see it on your celebration, which is 2 weeks from today. We're all done. So 3 things that influence the rate. Anybody?
Temperature?
Yeah, why? We just went through that, but
Higher
go
the
ahead, Damon.
temperature, the more kinetic energy.
Yeah, so as you increase the temperature, you increase the kinetic energy or the jiggles. And one of the keys with this, I don't know if you remember, Damon, when you're talking about it as far as the rate of a reaction, do you remember what you had to then say that's going to cause? It's going to cause
More collisions.
Yeah, so it all has to do with collisions. So it's going to increase the collisions. It's also going to increase the impact of the collisions or how hard they're colliding. And this is talking about atoms colliding, right? Or molecules and stuff. So looking down at the quantum scale. So higher temperature means you have more jiggles. And if everything's got more jiggles and giggles, you're going to be colliding more often and you're going to be hitting harder. And so that increases the reaction rate. All right, what's another one?
Catalyst.
Catalyst. That's why I'm dressed like this today, because we're going to talk about catalyst today. So I think that's page 3 of our notes. So a catalyst. This one's a big change. So temperature, it's about every 10 degrees, you double, 10 degrees Celsius, you double the rate, or half the rate if you're cooling it down by 10 degrees. That's like a rough estimate. A catalyst, this is like 1,000,000 to 1,000,000,000 fold. There is a limit to how fast the catalyst can work, because there are physical laws that limit how fast things can collide. And that's what limits catalysts to how fast they can go. But a catalyst, what a catalyst does is it aligns the reactants, so every collision is perfect. So a lot of collisions, right? We've all had collisions in our life, so every collision is perfect. I'm going to add one other piece here that we will be talking about when we get to page 3, and that is a catalyst lowers the activation energy. So you can just leave it like that. You'll know what that means in 2 pages. It is the only thing that can do that, and that has a big effect. So again, if you look at the study set, the activation energy was really small. It was like 5 kilojoules. And on the worksheet, the activation energy is like 100. And that change in activation energy, when there's a change in the temperature, there's a huge difference that happens. All right. What was the third thing that can make a reaction go faster?
Concentration.
Yeah, and so there's a couple different ways you can do concentration. You can either, and this is the idea of these tables, is when we double it, it doubles. So you're increasing, there's more stuff, so greater probability of colliding. You could also decrease the volume, that's changing the concentration, or increase the pressure. So to me, those are all the same idea. So more pressure means you're pushing it together, there's less volume, so there's a greater probability that they will collide. And that goes with these data tables. All right. So I'm going to give you guys a moment to try it, and then I will give you the rate law, and then I will pause because I want to make sure you have the rate law. So determining really step E goes with step F, and then I'll give you a chance to try the rest of it. So the rate laws are always that the rate equals K, and then the concentration raised to some power of each of the reactants. These powers, the question marks, those are the order of the reaction. I don't know who called it that, but that's how it's related. So let's look at the table, and it just takes practice. So you want to find when only one of your reactants changes. So here the fluorine doesn't change, and this changes by 3-fold. So we triple it, and if you look here, this goes up by 9. So it is second power or second order. So the idea is when we triple the NO, what power will give you a 9-fold change in the rate? Because nothing else is changing. The K is a constant and the fluorine's a constant. So 3 to what power equals 9? And the key to this one, it's 3 to the second power. So it's not third power, because that would be 27. So it's second order for the NO2. All right, to figure out our other one, our fluorine, we want to compare, in this case, the first one to the third one. So you have to, again, always look when only one thing changes. So if you look at the first and the third one, the NO2 doesn't change. The NO2 is staying the same, right? It's staying at 0.2. And so it's different every time. Sometimes you compare the second to the third, but here we double it and the rate doubles. So if we double and it doubles, that's first order. So when we double the fluorine, equals double the rate. This was 9-fold change in the rate. And so if it's a straight relationship, if you triple, it would triple, that's first order. And so this is our rate law, which again is just an algebraic equation for this experiment. So I'm going to pause this, give you a moment to try those two, and or you can take like a 5-minute break, but you should try them or look at the data table. But I'm going to pause this for a few moments so you can try it. All right. So hopefully you guys did that or you're back from your break. So determining the units, again, this is just an algebraic equation. So the key is getting this correct. So kinetics is not hard at all. It's just different and it's just number crunching. So, oh, sorry, that's not what I wanted to do. So we're going to plug it. You just, excuse me, plug in one set of data. We'll just do the first set of data. So 0.41 with the units. Don't let the units scare you. And so we're solving for K. And then we'll divide by these pieces. So the 0.20. And that is molarity. Your teacher did not label her tables well. That would be squared. And then the fluorine is 0.10 molarity. So this molarity cancels that one. And you punch it in your calculator, you'll get around 100. 2 sig figs. So that's probably why I don't have 102 or whatever it comes out to. And then you'll have either per molarity squared second or m to the minus 2, s to the minus 1. So I just write it as 100, respecting that that technically has 2 sig figs. And then determining the rate, our missing number here, we just plug into our equation using our now magic number and plugging in. And you should get my answer there. All right, any questions? It just takes practice. And so please do the study set. Please make sure kinetics ends up being that people do really well with it or they never put the time in. So just do it. You don't have to put that much time in. All right, so we're going to look at 0, first, and second order. There are other possibilities. We're just not going to deal with them. But in case like you decide to major in biochemistry and sometimes in organic chemistry and much higher levels, not like the first basic organic chemistry class, you'll run into kinetics because enzymes deal with kinetics. So 0 order, this is technically what it would mean. So it's a change in the concentration of A per time would equal K to the 0 order. So the change in the concentration of A, if we move T to the other side, since anything to the 0 order means it's just the number 1, that crosses out. You would have negative, it's a decay, so it's negative K times T. And change means final minus initial. So again, A sub 0 is always your initial concentration. And so it's a pretty simple formula. For first order, when you write this out, because this is still there without the AT A0, you have to do some fancy calculus stuff. So those who are taking calculus, I think it's second term here in Oregon, you end up with this formula. So we're not going to go through how to get there, but this is the formula we used. And this is why we're doing radioactivity this week, because it is always first order decay. So iodine 125 so our thyroid has iodine, not 125. 125 is radioactive. So radioactive is the study of nuclear chemistry, is every element on the periodic table has an unstable form. So like carbon 14, and it really has to do with the ratio of protons to neutrons. And we'll talk about that on Thursday. But this is telling us that they'll use a radioactive isotope to try to study it, because then they can take pictures of it because it's giving off radioactive particles that allow them to see the treatment. So this is our initial, and then this is our after 1 week or 7 days. So we'll do it as 7 days as our time. And it wants us to find the half-life. So I'll pause again. You're going to do this in 2 steps. You're going to first solve for K. So solve for K. and then solve for half-life. And if you notice, my answer uses the unit days. So don't go to minutes or seconds. It's going to be a long number because you can see this did not change by much yet. So I'm going to pause. And so again, you're using this formula first to solve for K. So go ahead and try it. Try something. All will be fine. All right, let's go ahead and solve this. So that's what you should have gotten for K, but your formula is this one. You're going to state your formula, AT over A0 equals negative KT, and then we just plug in. So natural log of final, which is the 6.3 is on top, and those are micrograms. This is one of the things that is beautiful about first order is it's a ratio, and so you can use any units. Zero order is not a ratio, so you have to use molarity, and same here. You must, when we do second order, because we're going to do one, you must use molarity. Here we can just leave it as micrograms because it's going to work, and then we divide by the 7 days, and that gives us our K value in per day. 2 sig figs, but you can keep the number in your calculator. And then your step 2 is this natural log of 1/2 equals negative K T 1/2. So we would just do negative log of 1/2 divided by, negative K, and that should give us around 63 days. Or if you did it in weeks, that would be what, 8, 9 weeks. All right. Does your answer make sense? Yeah, because in 7 days, in 1 week, very little decomposed. So in 1 week, very little decomposed or disappeared. So our half-life is much longer. So questions? All right.
Where did we get the 0.011?
That was my K value. Did you guys not get that for K? Yeah, I assume that's right because I just punched it in real quick. So yeah, I recommend, I'm sure there's people online who do these fancy things and tutors where they do it in 1 step, which I'm sure I could do that too, but I don't, it's easier to just break it into 2 steps. So solve for K, because then you also have K, because sometimes there'll be a part C where I'll have you do another kind of solving step. And so I also wanted to, oh, I thought the question was on here and it's not. I wanted to make a comment about this because it's on your next study set, is if I do a percent. So if a percent is given, you assume that your initial is either 100 or 1, depending how you think of percents, right? And so it's going to decrease from there. So it's always decaying from that. The other thing is you need to be careful about how AT is worded. AT is how much is left. After a given time. So I mention that because if you see where it says 25% is left, then 25 is your AT. But if it said 25% disappeared or decomposed, 25% is not the final amount. 25% is how much is gone. You're left with 75%. And so 75 would be your AT. So just be careful how they're worded. And I know that shows up on the next study set. And I thought it was going to show up here, but it does not. It shows up in Thursday's notes. Anyway, all right. Second order decay, when you go through the fancy integration stuff, you'll get this as the formula. And so to solve this, the temperature is extra information in this case because it didn't change. so you can ignore it. I gave you the value of K is 30, and the units are funky. Just go with what your units are. So this is just saying the molarity is flipped over. And so we're solving for time. And this is our initial, and this is our final. And I was really nice here because they're in molarity. So moles per liter is molarity. So we would just use this formula, and it tells you it's second order. It will always tell you what the order is. So we would just do 1 over. It has to be molarity because it's not a ratio. The 0.005 and 0.01. Now this is interesting because this is a half-life. We're going to be solving for the half-life. And I know that because half of it disappeared. So it's half the number I started with. And then that equals, and it just has to do with how the math works out. There is no negative here. So you can ponder that. And then times T. So you would subtract and then divide by the K value, and you would get my T. So I mention this page because, again, you're going to mostly be doing first order. Those of you who took Math 111, this is the application of natural logs, and E is the decomposition or decay of radioactivity. But there are other possibilities. And so I just wanted to mention, because I'm supposed to be teaching you this, and normally we would spend an hour and be practicing with our calculators. But there is a way to graphically determine if something is 0 first or second order. And just in this environment, and my patients probably, if something is 0 order, you're always putting time as the x-axis. Time isn't real, and so time is always independent of, right? And then the y-axis has to do with the concentration. So the amount that you have is dependent on the time. The thing is if it's 0 order, it is just the concentration of A. If it's first order, it's the natural log of the concentration. Sorry. And if it's second order, it's 1 over the concentration. And that's what these formulas were showing. And anytime if you have the absolute value, the slope gives you the rate constant. So it's actually a really cool thing. But it can be a really frustrating hour as we each figure out how to graph on our calculator or on our computers and stuff. But it's a nice relationship. So we're not going to actually do the graphing, but you do need to know the relationship that 0, this is a linear relationship. So you will end up with a straight line. First order decay is a natural log relationship, and second order decay is just an inverse relationship. All right, that's all I have for that. We're not going to worry about graphing. Just don't tell anyone. You guys are doing a second presentation and nobody else is, so I feel justified in not making us graph. All right, scan the sweat just like a cat. We're going to do reaction mechanisms now. These are really cool. And it is the myth that I've been perpetuating this whole past 2 or 3 terms, however long you've been with me. Most reactions are not 1-step reactions. Most reactions are 2 or 3 steps. People spend their whole lifetime, their whole career as a chemist, trying to figure out the steps in a reaction. In fact, no, this is not. That was like part of that's where the Nobel Prizes in chemistry will often be. So the ozone, the guy who won Nobel Prize for figuring out the whole ozone depletion, that was part of what he worked on, was the kinetics of it. When he was like 5, he had his aunt build a chemistry lab out of her bathroom. And so he was experimenting in his aunt's bathroom ever since he was 5. That's like dedication. All right. And what they do with these is they trap what are called intermediates. So first thing we're going to do is we're going to add up this equation. So here's our arrows, and anything that's found on one side they can cross out. So if you notice this fluorine, just as F, not the F2, it's on the reactant side and product side. So it crosses out. And it is what is known as an intermediate. It is something that is formed in one step. Sorry, I thought I wasn't recording for a moment. Formed in one step and used in a later step. Used or consumed in a later step. So it's not in the net equation. And so here we have NO2 and another NO2. So in our overall equation, there's two NO2s and there's an F2. And we end up with this funky thing, which is FNO2, which is probably highly reactive and highly toxic. But that's our equation. It is balanced, right? We have two nitrogens. Sorry, I said two, and I didn't write the two. So we have two nitrogens, we have four oxygens, we have two fluorines. All right, the rate law is the slow step. That's really the key to this, is what an intermediate is, and with the slow step, you will be told what the slow step is, and it's not just the slow step. See, mine are all losing their ink. So the slow step, the stoichiometry, so the coefficients become, sorry, my pens are all running out of ink. It must be time for the term to be over. Equal the order or the power. So we don't need a chart. There's two ways to know the rate law. One is the experiment, which is the chart, which you guys would have gotten to make one of those charts in lab with your very own data. Or you spend years trying to trap intermediates. So it's still written as rate equals K. And then we just look at the slow step and we just look at the reactants. So there's one NO2. So that would be first order. And there's one fluorine. So it's just first order with each of them. So the overall reaction does not tell you the rate law because there's two NO2s. The overall reaction tells you nothing with kinetics. So the molecularity is how many things are colliding. So how many reactants are colliding per step? And so in this case, they are bi and bi. That makes sense. Collisions of two things, that makes sense. The overall doesn't make sense because there would have to be two NO2s and a fluorine, and the probability of three things colliding at the exact same moment in time is pretty much impossible. These things are happening in femtoseconds. So does anybody remember what a femto is? So nano is a billionth. That's how fast your nervous system works. Femto is 10 to the negative 15th. So a million times faster than a nanosecond. So chemical collisions, and that is limited by the law of physics, how fast things can collide. And that's where it gets even more interesting, because once you go into the quantum level, which is vibrational, you don't have any limits. And that's what we don't get yet. And so once we're able to make that grasp that once we think outside of the box and stop thinking about material things, then we can start doing some really cool stuff. Somebody said something. I'll have to see it later. All right, we're going to do an energy diagram. And endothermic, you guys remember what endothermic means? Endothermic means your heat is absorbed. And so heat or energy, guess we're doing more energy. So this part is the energy, this level, and this is the reaction, the x-axis or time. All right. So heat is going to be absorbed. It means we start at some level down here and we're going to end at some level up here. You can write just the words reactants and products, or you can write that you're going to have NO2 plus fluorine reacting, and up here you're going to end at the very end with FNO2. So when I did one the other day, I just wrote reactants and products. Now, the key is, this is a question I have for major, because so there's going to be two humps. So there's 2 steps equals 2 humps, or 2 activation energies. So we go really high and it comes down. First step is slow. So step 1 gets a huge activation energy. So from here, from our starting point to the top of the hill, that's our activation energy. And then the second step's much faster, so it just has a little hump. The fast steps are fast. So it's like a roller coaster. You have to get up this really big hill and then we come down. So that is our EA2. It's much faster. That was our fast step. The activation energy is from where that step starts to where the top of the hill. All right, and then that's activation energy. Also, the difference between where you start and where you end, that is the delta H or the delta E. So that's the change. So from the reactants to the products, and this shows us it's endothermic. All right, now we get to do one more step here. Let's see if the pink will work. Do black for Rocky's sake. I have it down here, but we'll do it on this one, is we're gonna add a catalyst. So a catalyst lowers the activation energy. It does not change the beginning and end point. It just makes the whole thing go faster because it lowers the activation energy. So it cuts out the hill. That's my catalyst. So you can put your cat on there if you want. He's taking a nap. He just made a shortcut, which is what a cat would want to do. Cats are pretty smart. They'd rather take a nap, so they'll find the fastest way from here to there. It doesn't affect my other hump. I still have 2 steps. It just cuts this one down, and it is still endothermic. All right. So I'm gonna pause
someone asked
us.
a question.
Yeah, I can't
Asking
see
about-
the chat while I'm talking and recording, but I'm gonna pause us. I'm gonna let you guys try this next one, and I'll see if I can. All right. So we want to find the pieces that are going to cancel out, and that is the Cl, which makes sense because we write chlorine as a diatomic. But in the reaction, it does become a monoatomic, and then it reacts immediately because as a monoatomic, the halogens are extremely reactive. So that's going to be our intermediate, is the Cl, not Cl2. You can say 2Cl, and so they're going to cross out. And orange is just not going to work. Yeah, so Max, that's what I was saying. These pens, once they're dead, they're dead. Let's just stick with green today. So the chlorines cancel out, and they're the intermediates. There's another intermediate. Does anybody see it?
CCl3.
Yeah, so this guy is going to cancel out too, the CCl3. So he's also an intermediate. That also makes sense because you guys remember carbon made 4 bonds. So carbon's going to want to have 4 chlorines around it. And so somebody figured out the mechanism of how to get that. And so it only picks up 3 chlorines, and then it's highly reactive. And these fast steps, again, are happening super duper fast, like in those nanoseconds or picoseconds or femtoseconds. All right. And I think we're good. So we can do our overall has the chlorine, the Cl2, and the CHCl3. And those make sense because this is a carbon with a hydrogen and 3 chlorines, so it has 4 things around it. And then we end up with the HCl and the carbon tetrachloride. Then you can check to make sure your overall is balanced. We have 1, 2, 3, 4, 5 chlorines, and then 1 plus 4 is 5. We have a carbon, we have a hydrogen. So we are balanced. The intermediates are not in the overall. So overall, there are no intermediates. And again, this is people work their whole life, or to get a PhD is trying to figure out one mechanism. That was definitely not something I worked on. The rate law is based on the slow step. So you look at the slow step coefficients. And almost always the slow step is the first one, but not necessarily. So where am I in here? So the rate law equals K, and you're looking at just the reactant coefficients of the reactants. So K times the chlorine. Now, there is a way the products could be in there, and that would be if the slow step was not in the first step. And that just requires more algebraic rearranging, but it's really, for our purposes, you guys just need to see the big picture. And if you decide to specialize in this, then you can go to a higher level chemistry and do all the fun algebraic rearrangement. So that's it. It's a simple rate law. The molecularity is uni. So bi is if there's two reactants, and uni is if there's only one. So it's basically a decomposition that happened. Our slow step was it just decomposed, it broke apart into 2 chlorines. All right, our energy diagram is exothermic. So our starting point, our ending point, we're going to release heat or energy. So our ending is down lower. So we'll put our product, our carbon tetrachloride, and our reactant to start with is the Cl2. And how many humps are we going to have? 3, because there are 3 steps. So the number of steps determine the number of humps. The activation energy is always uphill because it's the energy to get it going. And so you can make it as big or little as you want. So the problem with this is I told you that the overall is exothermic. I didn't tell you what each step was, so that's kind of up to you. But this, from my starting point to the top of the hill, that is our activation energy. Endothermics are always much more dramatic because you have to end up high. And then it's kind of up to you if you want to come down and do each of your next steps. And then we come all the way down. And then they would each have a little itty bitty activation energy. So from their valley to the top of their hill. So there's like a little valley between each ones. Again, it's like a little roller coaster ride. All right, one other piece we want to label is, so we labeled the activation energies. We want to label the enthalpy change, and the enthalpy change is from where you start to where you end. So that's my change in H, my delta H, or delta E if you want to think of it as energy. And then we get to do the cat. So when you draw the cat, he does not change any of the platforms. Any of your starting and ending points, wherever you put them, they don't change. The cat just cuts out the hill. So that's going to be our catalyst. He just got rid of that hill. And that makes it go quite a bit faster. That's not a dotted line. All right. Questions? Again, you can type them in there. Somebody will read the question to me.
I just have one question. The states of matter are still staying the same, right?
The states of matter?
In the equation when we write it.
Yeah,
when we
so
write it out
yeah, I was
overall.
going to comment on that. So I kept emphasizing on the last test, states of matter are key. And that's because we were studying states of matter, and they are important, but in here you can leave them out. I'm okay with that. You can see on this first equation, I left them out. So yeah, thank you. They should be in there, be the correct answer. All right, one more page. So we're gonna talk about temperature, or review the temperature effect. So, and this has to do with activation energy. So we now talked about the activation energy, which is the energy to get over the hill. Temperature does not change the activation energy. The only thing that can change the activation energy is a catalyst. And that's why catalysts can change it. Like these graphs are nowhere near proportion. They're just a sketch to see what's going on, but it's not proportional. A catalyst makes it go 1,000,000 times faster, which you're not seeing this from there. And then before I move on, because I did have a real question for Major, is are there such a thing as camels with 2 humps? We end up making jokes. In Egypt, aren't they like there's different camels from different parts of the world?
I've only been on one with one. I don't know about
I think the Egyptian one. So Damon's like, no, there's ones that have 2 humps. Where are they? See, he's Googling it to see where they're from. They're obviously not from Egypt. How about 3 humps? There's none with 3. There's gotta be one.
The other one lives in Central Asia.
Okay. I wonder why that happened. Pondering. Interesting. All right, temperature, how and why is giggles. So you increase the kinetic energy, you increase the giggles, you increase the collisions and the impact of the collisions. So the force, how hard they're colliding. So temperature does have a significant effect. The value of R again, it is, so this will help you if you didn't do your worksheet, 8.314 e to -3 kilojoules per mole. And then this is our formula. And again, this can be done by graphing. And I went through a big debate for the past 24 hours if I was going to teach you how to do this with graphing. And my head said, we're good enough with all the math. It's the 9th week, and right, Major's having knee surgery, so he's thrilled that we're not going to be doing graphing. So with that, there is one more lab. There's actually 2 more labs. The one is class presentations, so being present and being a good audience. But the other lab, it's just going to have a lot of math and stuff. It's going to be due next week. So nothing's going to be due this weekend because it is a holiday weekend, and it is actually going to be a beautiful sunny weekend. Get all your jiggles and giggles and stuff out so that you can do your research and get your paper done if you like have nothing to do. But you all have something to do. You'll all find something to do. All right. So there'll be, right, the end is coming near. So if you want, you can do your research this weekend and write your paper. That is actually why there is no lab due. Or you can wait and do it next Tuesday and Wednesday like you guys are going to do. All right. There is a study set for Thursday, and there will be a study set for next Tuesday, but that's radioactivity, so that's not bad. All right, so here's our, just label your parts. There's our K1. We just need to change this to Kelvin. You have to always use Kelvin. Sorry, this constant is kilojoules per mole K. So this is our T1. And then this is our K2, and we're solving, sorry, I'm sorry, I didn't read my question. This is T2, because the 10 degrees Celsius, the rate constant is that. The 0 degrees is 273 Kelvin, that's T1. And so I'm going to pause, give you a chance to try these again, and then I'll go through it. And all right, or you can take a 5-minute break, or you can work on your worksheet. So our formula, we're solving for activation energy. You would state the formula, it's right there for me. So K2. And really this is all about using your calculator. My ears did that popping thing again. It only happens in our class. So a comment, I was making this during my office hours. You guys see a little ant? That's good. There's not going to be an earthquake today. You see the ants? Say thank you. No earthquakes today. There's also no food here, so I don't know where he came from. Probably my sleeve. All right. I was talking to Joey the other day, and I had a spider on my shoulder, and he was freaking out. It was just a little spider. Like, it's just a little spider, and he like could not talk to me. He just kept looking at the spider. I'm like, oh, go away. The comment though I was going to make is these sometimes K's are all over the place. K's are different for everything. And so these are positive exponents. Sometimes they're negative exponents. So just please be careful that you write it down. So don't rush and stuff like that. And then we'll we'll multiply this by the R. So there's our R. Go back to green. And then divide by 1 over, there's negative, T2, which is the 283. I highly recommend that you label your T1 and T2 so you don't mix them up like I almost did. And 1 over 273 Kelvin. You can put them in as separate steps. Just make sure you use your parentheses correctly. So this will be in parentheses, this will be in parentheses. And your activation energy is always a positive number. If you get a negative, it's just that you flipped something or you forgot the negative, but 51 kilojoules. And again, the R is a different R. That was just me underlining that. That's not negative. All right. Here we're going to calculate the temperature. So this I'm going to give as my K2. So that's my new number on top, 3.74 e to the 4th. This is wrong. This should just say per second. Sorry, because the other ones were. And then my 4.5 e to the 3rd per second. The EA and R will flip, so we'll multiply by R and we'll divide by the negative 51 kilojoules per mole. That's going to equal 1 over T2 minus 1 over T1. My recommendation is you put this in, and then when you get that whole answer, which we can do it, you'll move this over. So then you'll add 1 over T1. This is like, to me, I love doing algebra, so I love this. Once you add the 1 over T1, you have to then, the answer, you'll have to flip over. So that whole thing would be to the negative 1 power. That's going to give you Kelvin. Then you have to subtract 273 to get back to Celsius. One more piece. Does the answer make sense? Yeah. So it is a higher temperature than either of these other ones were in the first part. And so higher kinetic energy, more giggles means it's faster. More giggles increases collisions, increases rate, increases K. Right? So that's the whole idea when I ask you to explain. You don't have to write it as a sentence, but you can. Some of you have to write sentences. But if you have more collisions, the rate goes faster, your K value And so our K value was higher, which means the rate was faster, which means the temperature must have been higher. So if your temperature came out lower, again, it was somewhere you lost the negative sign. You just go back where you plugged here, you plug these in upside down or something. All right, that's all I got. So goodbye.